In this video, I want to talk about intermolecular forces, particularly dipole-dipole interactions and hydrogen bonding. So let's start with dipole-dipole interactions. This occurs usually between polar molecules. For example, consider the molecule acetone. It's a polar molecule, and the central carbon is double bonded to an oxygen atom, which has two lone pairs. Now the oxygen atom has a partial negative charge, and the carbon atom has a partial positive charge. Now what do you think is going to happen if that acetone molecule is placed nearby another acetone molecule? If that happens, there's going to be a dipole-dipole interaction. The carbon from the second molecule is going to be attracted to the oxygen of the first molecule because opposites attract. And so this negatively charged oxygen atom will be attracted to this partially positively charged carbon atom. And so this creates the dipole-dipole interaction. So keep in mind, when you're dealing with intermolecular forces, you're dealing with forces or interactions between molecules and not necessarily within a molecule. Let's consider another example, and that is carbon monoxide, which looks like this. The carbon bears a partial positive charge, and the oxygen bears a partial negative charge. And let's draw another carbon monoxide molecule next to it. So each of these molecules possess a dipole moment, and so you can call it a dipole. And so the interaction between one dipole with another is known as a dipole-dipole interaction. So that's an interaction between two separate molecules. And so this is the dipole-dipole interaction. And so those two molecules are attracted to each other. As you know, opposites attract. So they feel a force that will pull them together. Now, hydrogen bonding is a special type of dipole-dipole interaction. It occurs when hydrogen is attached to one of these three elements: nitrogen, oxygen, or fluorine. So let's use water as an example. So the oxygen of water bears a partial negative charge, and the hydrogen bears a partial positive charge. And so the oxygen of one water molecule is attracted to the hydrogen of another. And so these hydrogen bonds, or these special type of dipole-dipole interactions, they keep the water molecules held together. And so this is an H bond. It's between two separate water molecules as opposed to within a water molecule. Now whenever you have hydrogen bonding, what it does to a molecule is it increases the boiling point of the molecule, and also it increases the water solubility of a molecule. For example, ammonia has hydrogen bonds in it. And so ammonia is polar, and it's going to be highly soluble in water. Methanol has hydrogen bonds in it. You can see the OH bond. And as a result, it has a relatively higher boiling point compared to other molecules that do not have hydrogen bonds. And also the solubility of methanol in water is very high. Methanol mixes completely with water. Now let's compare ethanol and dimethyl ether. Which of these two molecules has a higher boiling point, and which one has a higher solubility in water? Ethanol, we can see, has hydrogen bonds, and so it's highly polar. Dimethyl ether is polar as well because of the oxygen and the fact that it has a bent shape. So it has a similar molecular geometry to that of water. However, notice that hydrogen is not directly attached to oxygen, and so it doesn't have any hydrogen bonds. Therefore, because hydrogen bonds have more intermolecular forces, or rather stronger intermolecular forces than regular dipole-dipole interactions, ethanol is going to have a higher boiling point. And as a result, it will also have a higher solubility in water due to the H bonds. The boiling point of ethanol is about 78 degrees Celsius. And for dimethyl ether, it's negative 23 Celsius. So you can see that this is a lot higher than that number. And so hydrogen bonds will greatly increase the boiling point and the solubility in water of a molecule. Now, what if we compare ethanol with 1-butanol? Which one has a higher boiling point? And which one has a greater solubility in water? Now, both of these molecules, they contain the hydrogen bonds. However, notice that the size of the hydrocarbon chain is not the same. For butanol, there's more atoms in that molecule, and as a result, in addition to hydrogen bonds, it's going to have more London dispersion forces. As a result, it's going to have a higher boiling point. So molecules with a large number of carbon atoms tend to have a higher boiling point than molecules with only a small number of carbon atoms, assuming everything else is the same. In this case, they both have the same OH functional group. Now, what about water solubility? Which one is more soluble in water? Now, you need to know that the OH bond is polar, but the CH bond is nonpolar. And water is a polar molecule. Like dissolves like. So molecules with the OH group will be highly soluble in water, whereas those with a CH group will not be soluble in water. Now, ethanol is soluble in water, and 1-butanol is still soluble in water. However, because of this nonpolar chain, the solubility will be less than that of ethanol. So ethanol is going to have a greater solubility in water because the nonpolar region is smaller than this bulky nonpolar region. In fact, the solubility of butanol, it's small in water. You can dissolve some of it, but not much. Another example is 1-octanol, where we have a total of 8 carbon atoms. Now, this molecule still has hydrogen bonds. However, because it has such a huge, bulky, nonpolar region, it's not soluble in water. In fact, it mixes with other nonpolar molecules like oil and things like that, but it doesn't mix in water because the OH part is soluble in water, but the CH part is not. The CH bonds are nonpolar, so they don't want to mix with water. And so whenever you have like small chain alcohols like ethanol or even methanol, these are highly soluble in water. But when you start adding a lot of CH groups or CH2 groups, then the solubility will decrease, but the boiling point will go up. So 1-octanol has the highest boiling point of these 3 molecules. But methanol has the highest solubility because it has the least number of nonpolar bonds. Now let's consider 2 other molecules. Pentane, which has 5 carbons, and neopentane, which also has 5 carbons. Now these are considered constitutional isomers because they have the same chemical formula, C5H12, but a different structure. They're connected differently. The molecular formula is the same, but the connectivity differs. So which one is going to have a higher boiling point since they have the same number of carbon atoms? If the number of carbon atoms are the same, then what you could do is look at the way it's structured. Straight chain alkanes have higher boiling points than branched alkanes. So pentane is going to have a higher boiling point than neopentane. Neopentane on the right is going to have a lower boiling point because it has less surface area when it's branched out. But if you have a straight chain alkane, it's going to have more surface area, and as a result, it's going to have more London dispersion forces. And anytime you increase the intermolecular forces, the boiling point of that molecule will increase. You increase the number of interactions between separate molecules. Now, none of these are soluble in water because they have no OH groups. A molecule that contains only carbon-hydrogen bonds like methane, ethane, or propane, all of these molecules, they're nonpolar, and so they do not mix with water.